Now we are going to see the case of comparing two means. We'll have two cases to do that, and that is assuming equal variances and assuming different variances. So the first one is this. Consider two independent random samples where x1 until xn are from a distribution with unknown mean mu(x) and unknown variance sigma x squared. And we will have the other sample that is y1 until ym, from a distribution with another mean that is unknown, and the variance is also unknown. We would like to estimate the difference in means, mu of x minus mu of y. This is our interest. And let's denote just lower cases for the x samples and for y. The point estimator is to estimate the difference in population means, we use the difference in sample means. So we are going to use x bar minus y bar. So remember that this is x bar is just 1 over n, the sum of all possible values of y. And the sample mean of y is 1 over m, the sum of all possible values of y. Okay, now the sampling distribution is this. We are going to see this. These first two statements are exact for normal populations and approximate for large samples from non-normal populations. The third statement is only approximate even for formula for normal populations, right? This one. Okay, the first one is for x bar minus x bar, using the central limit theorem and the difference of normal random variables, similar to what we did with the proportions, is normally distributed, and the mean is the difference of means, mu of x minus mu of y, and the variance is going to be the sum of variance. The variance of x bar is sigma squared over sigma squared of x, just to make it clear, over n, and the variance of y is sigma squared of y over n, the variance of y bar, of the sample mean of y. If we standardize these, x bar minus y bar minus the mean, the mean that is mu of x minus mu of y, and we divide this by the standard deviation, that is the square root of this quantity here, that is sigma square of x over n plus sigma square of y over m. This is approximately normal with mean 0 and 1. So these first two statements are exact for normal populations, and they are approximate for large samples from non-normal populations. Okay, to estimate the variance, since we don't know them, we are going to replace that. We are going to use the sample variance. So this is x bar minus y bar minus mu of x minus mu of y, and we divide by the sample variance here instead of the variance. In this case, this is not normal. This is a t distribution, and the degrees of freedom is this number that is called nu.